Hello everyone, this video is about support vector machine, which is the most powerful supervised learning algorithm that is applicable for both regression and classification problems. So in the previous videos we have seen that linear regression is applicable only for continuous or quantitative response variables in general, and there is also a linear relationship assumption between the covariates and the continuous outcome variable. If the relationship is going to consider nonlinear function of the covariates, manual specification of this nonlinear covariates or transforming the required input features or covariates is required. And on the other hand, logistic regression is applicable only for modeling categorical outcome variables. And logistic regression is also intrinsically a linear function of the predictors, specifically using the log odds or log transformation. But unlike that of this linear regression, which is limited only for continuous response variables, and that's of logistic regression, which is applicable only for categorical outcome variables, a support vector machine can handle both regression and classification problems. Specifically, the support vector machine that is applicable for classification is termed as support vector classifier, and the one that is applicable for regression problem is called support vector regressor. So unlike that of the linear models, that's of logistic regression or linear regression, which are strictly linear with respect to the parameters of interest, a support vector machine is in general nonlinear. If required, it can be just a linear when we use with a linear kernel. Otherwise, in general, a support vector machine is a nonlinear supervised learning algorithm that uses kernels to implicitly map the input data into certain higher dimensions. So these are the difference between this support vector machine and the standard linear models, that's of linear regression and logistic regression. So let's come to the definition of a support vector machine, or what is an SVM. So this support vector machine is applicable for both classification and regression problems. So with regard to the classification, or specific to a support vector classifier, the aim is to find the best separating hyperplane that maximizes the margin between the different classes. That in the classification problem we have a categorical outcome variable. So the interest in the support vector classifier is to find a certain separating hyperplane or separating, let's say, line that maximizes the distance between the different classes. And it depends on actually on a certain points which are called support vectors that define the decision boundary or the separating hyperplane or separating line. And actually these points are points that are closest to that boundary, or points that are misclassified. But those points that are not misclassified will not have any contribution to the decision boundary. So instead of all the observations that are included in a particular dataset, a support vector machine depends only on a certain points which are called support vectors. And these points or these support vectors are just points that are misclassified or points that are closest to the decision boundary. So in logistic regression, the aim is to separate the classes. But when you come to that of a support vector machine, or specifically a support vector classifier, the aim is not only separating the classes, but it separates the classes with the widest possible gap or the maximum possible gap between the different classes. So it does not simply separate the classes, but rather it separates the classes provided that there is a possible maximum gap between the different classes. And for a regression problem, that is the support vector regressor, instead of finding a strict decision boundary, it tries to find a function that keeps most of the data points within a certain margin of tolerance, which is called cube. So a support vector machine is in general a non-linear supervised machine learning algorithm, but it can be also linear. So now let's consider that of a linear support vector classifier, specifically the one that is applicable for classification problem. Then in the linear support vector classifier, the aim is to find a certain hyperplane that maximizes the margins for linearly separable data. So a linearly separable data is nothing but a data points that can be separated by a straight line. So the decision boundary for a linear support vector classifier is similar to that of a logistic regression model. Or for every generalized linear model, we have the linear predictor as the systematic component of those models. This linear predictor or linear combination of the covariates is nothing but W0 plus W1 x1 plus W2 x2 plus WP xp, or which can be written in matrix form like W transpose x. We can set it to 0, therefore this linear predictor is called the decision boundary, or that's of the decision hyperplane that separates the different classes. So this is the decision boundary for logistic regression. Similarly, this can be considered as a decision boundary for a linear support vector machine, which consists of that's of linear combination of the covariates. So in general, if this linear predictor is greater than or equals to 0, then we can say the predicted class is class 1, or let's say 1. And if this linear predictor has a value less than 0, we can say the predicted class is the second class, or let's say class 0. So here the linear support vector classifier aims to find the value of these parameters W0, W1, W2 up to WP that minimizes a loss called hinge loss. In the case of logistic regression, there is a log loss, or what we call cross entropy loss, but in the case of support vector classifier, the aim is to minimize the hinge loss. And this hinge loss can be written in this form, just the sum of the maximum of 0 or 1 minus yi times W transpose xi for all I running from observation 1 up to observation n. So the aim is just to minimize this function and obtain the value of the parameters, which include the bias and that's of the weights associated with the different covariates. So with this definition of loss function, for example, let's yi be 1, and let's this linear predictor has a value greater than 1. Now if yi is 1 and if the linear predictor has a value greater than 1, then the product yi times W transpose xi will be greater than 1. Then if it is greater than 1, we are going to consider the maximum of 0 and 1 minus a number greater than 1. Then the maximum of 0 and 1 minus a number greater than 1 is 0. Then the loss will become 0 if yi is 1 and if the linear predictor predicts a value greater than 1. Then in that case the loss will be 0. And again, if I assume yi to be 1, if this linear predictor W transpose xi predicts a value between 0 and 1, then 1 times a value between 0 and 1 will be a value between 0 and 1. Then here we have 1 minus a value between 0 and 1. It will provide a value between 0 and 1. And finally, if we take the maximum of 0 or a value between 0 and 1, then in that case it results a value between 0 and 1. Then for that case the loss or the hinge loss will be between 0 and 1. That is where yi is 1 and this linear predictor predicts a value between 0 and 1. Then automatically the loss will be between 0 and 1. And again, if yi is 1, but if this linear predictor predicts a value less than 0, that's negative, then 1 times a negative number, the product will be negative. Then 1 minus that's 1 minus a negative number, this will be 1 plus a positive number. Then 1 plus a positive number will yield a number greater than 1. Then in that case the maximum of 0 and a number greater than 1, then the loss will be a number greater than 1. And if yi is 0, regardless of the value of the linear predictor, if yi is 0, regardless of the value of this linear predictor, this component will be 0. 1 minus 0, that will be 1. Then maximum of 0 or 1, the value will be 1. Therefore, this is the characteristics of what we call hinge loss. Or if we look at here in the plots, if the raw model output, this raw model output is nothing but W transpose xi, that is the linear predictor, or this function. If this function predicts a value greater than 1, then automatically the hinge loss will be 0. Here the hinge loss is represented by the blue line. Therefore, if the linear predictor predicts a value greater than 1, the hinge loss is automatically 0. But if it predicts a value less than 1, then we will have a loss function which is just a linear function of the raw model output. The raw model output. Specifically, if the raw model output is in between 0 and 1, the hinge loss is again in between, let's say, 0 and 1. But if the raw model output is less than 0, in that case the hinge loss is also a value greater than 1. A value greater than 1. But for that of logistic loss, just for every raw model outputs will have some value. But here for all values, for all the values of the raw model output which are greater than 1, the hinge loss takes the value 0. But the logistic loss or the log loss will have some value. Therefore, this is the characteristic of the hinge loss that the support vector classifier aims to minimize in order to obtain the parameter estimates of the decision boundary. If we consider an L2 regularization, or that's of a rich support vector classifier type, then we are going to add here just that's of the sum square of the weights, or the L2 norm of the weights. And like that of a logistic regression model, here the regularization parameter is multiplied with that of the loss function, or the hinge loss. So C is a regularization parameter which should be greater than 0. Therefore, if C is larger, that means we are more maximizing, that's of minimizing, that's of the loss function. But if C is smaller, in that case, we are more minimizing, that's of the penalty. So what is the difference between linear support vector classifier and logistic regression? Now, here let's consider this picture. In this figure, suppose we have two classes, one denoted by blue, let's say for class 1, and the other, the one that is denoted by red, let's consider it as class 2. Now, if we fit, let's say, a logistic regression model, we could have a decision boundary or a logistic model representing line A, or we could have a logistic regression model representing B, or a decision boundary represented by B, or even we could have a logistic regression model that is represented by C, or a decision boundary C. Now, if we look at the performance of these three decision boundaries or these three logistic regression models, it's just all of these three models classify the two different classes with 100% accuracy. Therefore, A classifies both the blue and red points perfectly, and B classifies the same, these two different classes perfectly, and C also classifies these two different points or these two different classes perfectly. Therefore, all these three models have an accuracy of 100%. But if we inspect it very closely, we can see that, for example, the decision boundary represented by A is close to the red points, or let's say class 2. And if we consider that of the decision boundary of B, it is close to that of the blue points. And if we consider that of the decision boundary represented by C, now it is close to both the blue and red points. Therefore, for example, if we consider, let's say, if we consider decision boundary A, if we have a certain point somewhere around here, if we have a certain point where the pointer presents, this could be classified as blue. But this point is far from blue, but it could be near to that of the red points. And again, if we consider that of the decision boundary of C, if we have a certain point somewhere around here, let's say somewhere around here. Now this point, let me make here just. Now if you consider this point, now this point is very close to the red points. But if we consider this decision boundary C, then this point would be classified as blue. And the same is true for that of B. If we have a certain point, let's say, around here, which is far from B, is it's going to be classified to that of the red points. But this point is very close to the blue points. Therefore, even if these three decision boundaries have an accuracy of 100%, their performance in making the prediction may be poor. Now let's consider that of a support vector classifier. Now with the same points, let's say this blue and red points, a support vector classifier aims to maximize the margin the margin between the different classes. So the support vector classifier considers two hyperplanes. One, a hyperplane for the first class, let's say for the blue points, and another hyperplane for the red points. Then with these two hyperplanes, it tries to maximize the margin or the distance between these two hyperplanes. So the support vector classifier decision boundary would be represented by this broken line. Now this broken line is far from the blue points, and at the same time it is far from the red points, and the distance that this broken line or this decision boundary found from that of the red point and the blue point is equal, because it maximizes the margin between the different classes, and the decision boundary lies in the middle of the margin. And another thing here in the logistic regression model, all these points will have a contribution in estimating the models of A, B, or C. But when it comes to that of a support vector classifier or a support vector machine in general, instead of all the observations, it depends only on a certain points which are closest to the classifier, or those points which could be misclassified. So for example, for this data, points that are closest to this decision boundary are this point, one red point, and we have two blue points. These 3 points are called support vectors. So this decision boundary or the broken line depends only on these 3 points, this one red point and these 2 blue points. So support vectors are nothing but points that are closest to the decision boundary or points that are misclassified. For this plot, there is no point that is misclassified, but there could be. For this case, there are no misclassified points. So the support vectors are just those points that are closest to this decision boundary. So all the other points that are not misclassified, for example, these are not misclassified, will have no contribution in estimating this decision boundary. Similarly, these red points are not misclassified, and these are not near to or closest to that of the classifier. Therefore, these red points will have no contribution in estimating this support vector classifier decision boundary. Therefore, the difference between this linear support vector classifier and logistic regression is that just the support vector classifier not only classifies the data, but it also classifies the data with the maximum margin, or by maximizing the margin between the different classes. So of these points A, B, C, or of these 3 decision boundaries, this line or this decision boundary could be better for making prediction. Therefore, a point somewhere here is going to be predicted as blue. But if we come to here, let's say a point here, if we consider decision boundary B, a point here would be misclassified as red, where it is just near to that of the blue points. But here, when you consider in the linear support vector classifier, this point will be classified as of blue, because it is near to the blue points. So in linear and logistic regression models, all the points contribute to the parameters. But this is not true for support vector machines in general. Only points that are incorrectly classified or points that are closest to the boundary contribute in estimating the parameters of the decision boundary. And these incorrectly classified examples or points that are closest to the boundary are called support vectors. Therefore, if an example is not a support vector, or if an example is not misclassified, or if an example is not close to the decision boundary, therefore that example will have no contribution in the estimation of the decision boundary. And how close the support vectors are to the boundary is going to be controlled by the regularization parameter C, which just balances the trade-off between the margin and the classification error. The margin and the classification error. Then here, for example, if the margin is more wide, misclassification could occur. Therefore, the classification error will be larger. But if the margin is narrower, misclassification will be low. Therefore, the misclassification error will be the lowest. So the regularization parameter C just makes a balance in between that of in maximizing the margin and that of minimizing the classification error. So now let's see the practical example regarding this support vector classifier. Here I have written some helper functions to make a certain plot. It's not that much required, but we are going to use just to make certain plots. So these are just certain codes for making certain plots or figures. So now for illustration purpose, let's just generate a certain synthetic or artificial data. And this data is going to be generated using the make blobs function from a scalar dataset. So let me just simply run this. Now the data is being generated. Now the data is generated. So here, for example, we can see X. Now X has two features, 1, 2. We have just generated 100 observations, or I can see X.shape using the method. Here I have 100 observations or examples and 2 features. Similarly, here I have generated Y. Now Y is a binary variable taking the values 0 and 1. If I check again on the shape, I have 100 observations. Therefore, I have a single outcome variable Y assuming 2 values 0 and 1, and I have inputs data with 2 features, let's say x1 and x2, and with 100 observations. Now let's plot this data using the function plot data. This is the function that I wrote for making a plot. So by calling this function, I have to run it first. So let me plot it. If I run it, so here the outcome variable has 2 classes, 0 and 1. The class 0 is denoted by these blue points, and the class 1 are denoted by these green points. So here the objective is to separate these blue points from the green points. Therefore, here clearly we can separate these 2 different classes, or these 2 different data points which are colored by blue and green using just a straight line. Therefore, such data is said to be linearly separable data, because the data can be classified by a straight line. If we have a certain straight line, something like here, therefore the data can be separated by such a straight line. Therefore, we call such data as linearly separable. But in practice, we will not have a linearly separable data. But just for illustration purpose, let's consider linearly separable data like this. Now, by calling the function train test split from a scalar model selection, let us split this input features data and output data into train and test sets. So train test splits X, Y with a test size of 30%. 70% will be considered for the training data and 30% will be considered for the test data. So let me run. Now splitting the data is done. So if I check just extract, here we have the data. Instead, it's better to observe the shape. You see here the test size is 30%, therefore 70% of the observations belong to the train sets and 30% for the test sets. So since we have 100 observations, exactly 70 observations belong to the train set, and the remaining 30 belong to that of the test sets. Now, since this data is linearly separable, we can simply use logistic regression model, just fitting the outcome y on the two features x1 and x2. So the logistic regression model for two features could be written like log of the odds probability of success divided by probability of failure is w0 plus w1 x1 plus w2 x2. Or the probability is nothing but the probability of success, or the probability of the outcome of interest is a sigmoid function of the linear predictor. W transpose of x is nothing but the linear predictor w0 plus w1 x1 plus w2 x2. So if this linear predictor, or if this logit value has a value greater than or equals to 0, then the sigmoid function will be greater than or equals to 0.5, then the predicted class will be class 1. And similarly, if this logit value, or if this linear predictor has a value less than 0, then the sigmoid function will have a value less than 0.5. In that case, we can assume the predicted class as 0. So let's fit this logistic regression model. So to fit this logistic regression model, we need to import the logistic regression class from a scalar linear model, as we have seen in the previous videos. So first we have to instantiate our model of interest. And we have assigned this instantiated model to the object name, let's say logistic reg. So if I run this, I have to import this. I have to run. Now it is imported. I have to run. Yeah. Now the logit model is instantiated. As we have seen before, it is not fitted yet, but we have instantiated, or we have created a certain container where our trained model is going to be stored. So as we said before, just by default it has a penalty of L2, right? The logistic regression model in scikit-learn has a penalty of L2, or it is just a rich type of logistic regression model. Now let's fit. To fit the model, we need to call the method fits over the instantiated model and supply the training data, x train, y train. So now the training is done. As usual, just the parameters are the same, but training is now fitted, but previously it was not fitted. Let's see the parameter estimates. Once we fit this logistic regression model, we can extract the parameter estimates using the attributes intercept to obtain the bias, and that's of cof to obtain that of the weights associated with the two different covariates. So let me run it. Therefore, the bias of the logit model is minus 0.147, and the weights associated with the first input feature x1 is minus 1.32, and the one that is associated with the second input feature is minus 1.03, let's say 5. So the model, or the decision boundary, will have something like this one: minus 0.1470, minus 1.3204, x1 minus 0.0346 x2. Therefore, if the sign of this linear predictor is positive, the predicted class can be considered as 1. If the sign of this linear predictor, or if the value of this linear predictor is negative, we can consider the predicted class as 0. So this is the model that is estimated. Therefore, whether this linear predictor is positive or negative, then the sigmoid function of the linear predictor will be greater than or less than 0.5, which indicates whether the predicted class is 1 or 0. So let's see the train and test performance. Here, this data is clearly linearly separable. Therefore, our logistic regression model or the logit model could be better. So, by calling the method score over the trained model and supplying the training data, we can obtain the train performance. And again, by calling the score method over our trained model and supplying this test data, we can obtain the test score. Therefore, here clearly the train and test scores are 100%. That means the logistic regression model perfectly separates these two different classes. So for this data, the logistic regression model is enough because it can separate these two different classes with 100% accuracy. So now let's consider a linear support vector classifier. So in the linear support vector classifier, the decision boundary is just this linear predictor, which is the same with that of the logistic regression model. So here we can write this linear support vector classifier as f of x equals w transpose x plus w naught. W naught is the bias term or the intercept of the model, and here w consists of the weights associated with the different covariates that can be included in the model. And here actually the weights associated with the different covariates can be obtained as the sum of alpha h, yh, xh. Xh is our input data, yh is our outcome, alpha h is called duality coefficient. And these weights are actually dependent only on the support vectors. Here look, h is an element of only the support vectors. All other points which are not support vectors will have no contribution in estimating these weights. And the same is true for that of the bias term. Here we have yh minus w transpose xh. H an element of the support vectors. And here 1 over SVS is nothing but 1 over number of support vectors. Therefore, those points which are support vectors have contribution in estimating these parameters w and w naught. So if the function f of x is non-negative, then the predicted class could be class 1. If this function is negative, the predicted class could be the second class, that is class 0. So now let's import this support vector classifier method from sklearn SVM. We need to import from sklearn SVM, import SVC. But here, as we saw before, this logistic regression and linear regression are just imported from sklearn linear model because they are specifically linear with respect to the covariates included, because they are a linear function of the covariates, or they are intrinsically a linear function of the covariates. So if this function is non-negative, the predicted class is class 1, otherwise it's 0. So let's import the SVC from this from the required, also from the corresponding package sklearn SVM. So the linear support vector classifier with two features can be written as w0 plus w1x1 plus w2x2. This wi is not wi, right? This is just w1 but xi1. Yeah, it should be w0 plus w1x1 plus w2x2. So the i's should be for the inputs Otherwise, the parameters are constant parameters or global parameters. So once we import the class SVC, we have to instantiate our model of interest, which is the support vector. So for now, by default, there is a linear kernel, but for now, let's specify this kernel equals linear, because we are focusing now on linear support vector classifier. So here, if I run here, for example, as usual, it is not fitted. This, we have just instantiated our linear support vector classifier, but it is not fitted yet. So the regularization parameter C is by default 1. The kernel type, it is linear. That means the model is something like this. Degree, gamma, these are other parameters required. If you are interested, you can go to the documentation and explore. For example, here the default value for the regularization parameter is 1, and the default kernel is RBF, which is called radial basis function. We'll see later. And here degree and gamma, these are other parameters, but you can look at the documentation here. The documentation is self-explanatory, so if you look at it very closely, you can understand what each parameter stands for. So we have instantiated our linear support vector classifier. So let's fit as usual on this instantiated model. We need to call the method fit and pass the training data x train and y train. So let me run it. Now the model is fitted with the specified parameter. The penalty or the regularization parameter is 1. The type of kernel is linear. Other parameters for now, let's ignore. Let's get the bias or intercept term of this linear support vector classifier. We need to call the method intercepts, like that of calling the intercept in the linear regression model and logistic regression model. So if I run it now, the bias term for the linear support vector classifier is 0.609, and the weights associated with the two covariates are minus 0.44 and minus 0.64, let's say 8. So the decision boundary is this one. Therefore, this decision boundary and the ones that we obtain when we use the logistic regression model are different. Here, this model is estimated using all the points included in the training sets. The training set has 70 observations. Therefore, all these 70 observations have a contribution in estimating this decision boundary. But in this case, in estimating this decision boundary of the support vector classifier, all the points do not have a contribution. Only some of the points, which are called support vector, will have a contribution in estimating this decision boundary. We can also obtain the duality coefficients if we are interested, and let's see. Now, totally here in the training sets, look, in the training sets here we have 70 observations, but all these 70 observations will not have a contribution. Only some of the points, which are called support vectors, will have a contribution in estimating the decision boundary of the support vector classifier. So let's see the support vectors using the attribute support vectors. If I run it here, look, we have 1 observation, 2 observation, 3 observation. In the training set, we have 70 observations, but of those 70 observations, only 3 points contribute in estimating this linear support classifier decision boundary. Therefore, only the position of these support vectors or these 3 points matters and any correctly classified point that is far from the margin will have no impact in the estimation of the decision boundary. This is because the points do not have a contribution in the loss function that the model aims to minimize. Therefore, points that are far from the margin will have no impact as long as they do not cross the margin. So only these points contribute to this linear support vector classifier. Now let's see the train and test performance of our support vector classifier. In the trained model SVC, we need to call the method score and pass the training set to obtain the training score, and we need to pass the testing sets in order to obtain the testing score. So if I run it now, like that of the logistic regression model, the linear support vector classifier has a 100% accuracy in both the training and testing sets. Therefore, both of the models are equally effective in classifying the two different classes. Therefore, both this logistic regression and linear support vector classifier has a 100% accuracy in both the training and test performance of classifying the two different classes. Now the question is, which one is better? So to answer this, let's compare the decision boundary of the linear support vector classifier and the logistic regression model. For that, just I have written a certain helper function plot SVC logistic db. Here is the one that I showed you at the beginning of the video. This one is just a simple function used to plot the decision boundary from the support vector classifier and from that of the logistic regression model. So I just need to call that function. So here let me plot first that's of the logistic regression model. This line of regression is nothing but the one that we have trained using the logistic regression, this model, right? The one that is estimated using the logistic regression model. So this red line represents the logistic regression model decision boundary. Therefore, this line perfectly classifies the blue and the green points with 100% accuracy. And let's plot also that of the support vector classifier. That is, let's plot this model, the one that is estimated using the support vector classifier, specifically the linear support vector classifier. So if I run this now, look, now this support vector classifier considers two hyperplanes. One hyperplane for one of the class, let's say for the blue points, another hyperplane for the green points. And within these two hyperplanes standing for the different classes, it aims to maximize the margin. Therefore, the line or the decision boundary that maximizes the margin between the two different hyperplanes standing for the different classes is this line, this solid line. Therefore, again, this solid line perfectly classifies the blue and the green points. Therefore, the accuracy of this support vector classifier is again 100%. Therefore, is there any difference between this line and this line? This is the logistic regression decision boundary, and this is the support vector decision boundary. It seems there is no difference, but let's plot together for observing the difference between the two decision boundaries. So again, I use the same function and include this support vector classifier and logistic regression models that we have trained already before. So here the red point, the red solid line stands for logistic regression decision boundary, and here the solid black line stands for that of the support vector classifier decision boundary. Now the difference between the two decision boundaries is clear. Therefore, for example, if we consider, let's say, if we consider logistic regression model, and if we have a certain point somewhere around here, let's say, this point would be classified as green, but compared to that of the blue points and the green points, this point is near to the blue points. So if we consider logistic regression, this point would be classified as green, but in fact it is more close to the blue points. Similarly, if we consider here, now this point would be more close to the that's of the green points, but based on the logistic regression decision boundary, it could be classified to the blue points. Therefore, the support vector classifier rather aims to maximize the distance from the hyperplanes standing for the different classes. Therefore, if we have a certain point, this will be automatically classified as green based on the support vector classifier. If we have a certain point around here, this point will be classified as blue based on this support vector classifier decision boundary. But this point, the point that I am pointing, this point would be classified as green if we consider that of the logistic regression decision boundary. Similarly, this point would be classified as blue if we consider that of the logistic regression decision boundary. Therefore, the support vector classifier aims to maximize the margin between the two different classes. Now let's generate another new data set similar to the previous one, and let me plot it. These another plots. Again, this is linearly separable, but compared to the previous data that we have generated, here the distance between the different classes is somewhat narrow. So again, let's fit a linear support vector classifier and logistic regression models again for this data. So we need to split into train and test. As usual, let's instantiate our linear support vector classifier and then train our model, and let's get the score. Again, here clearly this data is also linearly separable. It's linearly separable because a straight line that passes through here can separate these blue and green points. Therefore, the linear support vector classifier has a 100% accuracy in separating these two different classes in both the training and testing sets. Let's fit a logistic regression model. Instantiating the logistic regression model, fitting the model, and let's get the score of the training set and the score using the test sets. Again, the logistic regression model also perfectly classifies these blue and green points. Let's plot the decision boundary of these two models together, like that of this one. In this case, the two different classes have a larger difference, larger separation difference between these 2 points, these two different types of points. But here, the separation space between these blue and green points is somewhat narrow. So let's plot these new data sets. This is the data. So when we fit a logistic regression model, the logit model is represented by this red solid line, and the linear support vector classifier is represented by this solid black line. Now this point is inside the margin, and this point is close to the support vector classifier decision boundary. Therefore, this is a support vector. Similarly, these 2 points are also support vectors. Therefore, similar to the previous data sets, this one, again here we have 3 points which are support vectors, or 3 points which are closest to the support vector decision boundary. So if we are interested, we can look at the support vectors, right? 1, 2, 3. The first, let's say for example, minus 2.19, 3.0, minus 2.19, minus 2.19 is something around here, and 3.0, this point, right? The first point, this point is this point, and 0.13, 1.5, 0.13, and 1.5 is this point, right? And the third one, minus 1.99 and 1.53, minus 1.99 and 1.53, minus 1.99 and let's say 1.53, this point. Therefore, these three are the support vectors for our support vector classifier decision boundary. So here, just these support vectors are nothing but points that are misclassified or points that are closest to the decision boundary. But those points that are not misclassified, or those points that are far from the decision boundary, are not support vectors, and they do not have any contribution in estimating the decision boundary of the support vector classifier. We can also look at the parameter estimates if we are interested. The bias, the weights associated with the two covariates is this one, and the bias is also this one. Now let's see the role of the regularization parameter C. The role of the regularization parameter C, which makes a balance between maximizing the margin and minimizing classification error. Here we have C, which plays the role of just balancing, that's of maximizing the margin between the different classes and minimizing that of the classification error, or minimizing misclassification. So here, now when the regularization parameter is small, it focuses on maximizing the margin. When C is small, if C is small, it tries to maximize this margin. Then that means, for example, for this case, this point is inside the margin. Then for this model, for example, we can assume that C is somewhat small. The regularization parameter is somewhat small. That's why this point gets inside the margin. And even some of the points may be even misclassified. But as much as possible, we need to minimize that misclassification or misclassified points, or we need to minimize the misclassification error. So when C is small, it focuses on maximizing the margin. The margin, or this line, the difference between this line, this broken line, and this broken line is going to be maximum. So this will be attracted to this side, and this one will be attracted towards this side. Then in that case, some of the points will be inside the margin, even some of the points could be misclassified. So when C is low or small, it focuses on maximizing the margin between the different classes, and some of the support vectors may lie inside the margin, and those support vectors that lie inside the margin are still considered as support vectors. And even there could be some points that are misclassified. There could be some points which could be misclassified. So when C is low, that means there is some tolerable error to let's say to consider some misclassification or overlap. So when C is low, again, just the model, or let's say the decision boundary is somewhat simple, or if it is extremely low, the decision boundary could be an underfitting decision boundary, or the model could be underfitting. On the other hand, if C or if the regularization parameter is high, then in that case it penalizes misclassification heavily. Then the model tries to classify every point correctly. Then in that case only the support vectors exactly on the margin are going to be used. But if C is extremely high, it will create very narrow margin and the model may tend to overfit. That means the model may have a good performance in the training set, but its performance on the test set could be bad. Therefore, in general, the regularization parameter C controls the trade-off between having a larger margin or having a simpler model and classifying points correctly, or just having a low training error. Therefore, we can specify the value of C in the support vector classifier by adding the optional parameter C equals a certain number. C equals a certain number. So here we have these points, for example, and by default here, as we have seen before, in our, let me instantiate here again just to see the parameter of interest. Now see, it is by default 1. So let's change this value and refit our model. C is 1, let's increase to, let's say, 100. By default it was 1, but let's increase to 100. And let's see the accuracy of the model. Now when C is 1, the model accuracy for the training and testing sets was just 100% for both. Again, when we change the regularization parameter to 100, again the model accuracy is 100% for both the training and testing sets. Let's see the plots and let's observe the difference. Look, now this point, because C is now large, then in that case the margin is going to be narrow. Then this line, which was previously around here, is approached to this point. Initially here, when C is 1, the line, the separating hyperplane for the green points is here. But when you change C into 100, this line is attracted towards this point. Therefore, this support vector lies on the hyperplane that stands for the green points. So it becomes like this. Therefore, when C is large, it penalizes misclassification heavily and tries to classify every point correctly. But a very large C may lead to the problem of what we call overfitting. So the appropriate, or let's say the optimal value of C should be determined by using that of the hyperparameter tuning procedure that we have considered in the linear models, using that of the grid search algorithm. So this is just a linear support vector that we have considered before, because the data can be separated by a linear model, or simply by a line that is represented by a straight line. So now let's consider the kernelized support vector classifier or nonlinear support vector classifier. Nonlinear support vector classifier. So the datasets that we have considered before are all linearly separable. In that case, a perfect decision boundary exists, or a decision boundary that perfectly classifies the different classes exists. But in reality, we will not have linearly separable data. So what if the data have some amount of overlap or mix of the different classes? Then in that case, the support vector classifier looks for a hyperplane that maximizes the margin and minimizes the misclassification error as much as possible. So support vector classifier, it's extremely powerful, especially when it's combined with what we call kernels, and specifically when it's combined with that of nonlinear kernels. So now here let's generate a new datasets. Specifically, let's generate this dataset using this make circles function from a scalar dataset, and let me show you here x. Again, we have two features and we have 100 observations. Okay, so this data seems the same with the previous one, but in fact this is not the same with the one that we have considered in the previous cases. So let's plot this data and see how the data looks, and let's determine, or let's look whether the data is actually linearly separable or not. Now here the class 0 is represented by the blue points and the class 1 represented by the green points. Therefore here clearly these 2 points, or these 2 types of points, cannot be classified by a straight line. Therefore this data is not linearly separable, rather it is a non-linearly separable data, or we have to find a model which is not linear. Therefore this data is not linearly separable. Therefore, for example, for this data, if we fit a logistic regression model, that logistic regression model will have an accuracy, let's say, around 50%, just like that of a random model. And again, if we consider linear support vector classifier, again, that linear support vector classifier will have maximum an accuracy of, let's say, 50%, because this data is not linearly separable. It's not linearly separable. So let's fit now, again, like that of the previous one, let's fit a linear support vector classifier and a logistic regression model, and let's see how the decision boundaries look like. So here for the support vector classifier, here I instantiated here, and in that I call the method fit and give just the data x, y. Here there is no need of just separate, because we are interested in looking how this how the decision boundary looks to separate these blue and green points. So for now there is no need of separating, or let's say there is no need of splitting the data into train and test. Just let's fit our linear support vector classifier and logistic regression model on the whole dataset. So SVC with linear kernel dot fit. Here this is the code for fitting that of the support vector classifier, which is specifically linear support vector classifier, and this one is the logistic regression model. So let me run. Now both of the models are trained. Now let's plot these trained models and let's see the decision boundaries. If I run this plots, it could be something like this. Now the red point is the logistic regression model decision boundary. Here the solid black line is that's of the decision boundary of the linear support vector classifier. Therefore here clearly these two lines couldn't separate these green and blue points. These green and blue points. And another thing here, for example, since it is not linearly separable, all the points for this support vector classifier, all the points have a contribution. But this model is actually poor because it couldn't classify these blue and green points in a proper way. And let's check just here the accuracy of the models. Let's say SVC, and it says score. We have already, let's say, X and Y. Let's say the support vector classifier accuracy, and let's consider that of the logistic regression accuracy, LGR. This is the training accuracy for the support vector classifier. This is the training accuracy for the logistic regression model. You see now the support vector classifier has a 68% accuracy, and the logistic regression model has nearly a 50% accuracy, because this data is not linearly separable. Therefore, those linear models in general are applicable for linearly separable data. Otherwise, if the data is not linearly separable, this linear supervised learning algorithms like logistic regression or linear support vector classifier would not be that much appropriate. So using a linear hyperplane for this data is not feasible to separate the two classes. So one idea is just to project the data into certain higher dimensions to make a linearly separable, right? For example, just here this data is expressed by x1 and x2, but instead of x1 and x2, what about if we include another point, let's say x2 square or x1 square? That means representing this two-dimensional data using a three-dimensional point or three-dimensional data. But here we don't know which feature to add, whether it is x1, x2, especially if we have a large number of input features, which feature should be added, we don't know. And then as the other, when we have a large number of input features, therefore adding many features, like considering all possible interactions, could be computationally expensive. It could be computationally expensive. So regarding that of support vector machine, there is a kernel trick, and specifically that considers nonlinear kernel functions, which allow us to learn without actually computing the new representation, or without just representing a two-dimensional data into three-dimensional, or a two-dimensional data into certain larger dimensional representation. And basically there are two common ways with this support vector machine. One is called polynomial kernel. This considers all possible polynomials up to a certain degree of the original features. It could be up to second degree polynomials, let's say up to fifth degree polynomials, and so on. And there is also another most common kernel function called radial basis function, or what we call Gaussian kernel. This Gaussian kernel considers all possible polynomials of all degrees. The polynomial kernel considers only all possible polynomials up to a certain degree, but the radial basis function just considers all polynomials of all degrees. And actually the importance of the features will decrease for higher degree representations. So for nonlinear or kernelized support vector classifier, the model is expressed something like this form. F of x equals the sum of alpha h y h k of x h x h runs for those points of support vectors plus w naught, and this the kernel function of xh and xi is expressed as an exponential function of this term, having just e to the power of minus gamma times the second norm of the difference between xh and xi. Therefore, this model is clearly nonlinear. Here we have the parameter w naught, but we couldn't obtain the weights associated with the different covariates because they are nonlinear functions. And here gamma represents the kernel width, how far a certain point affects that of the decision boundary. So if we record that of the linear support vector classifier, in that case we have w transpose x plus w naught. So this can be written as the sum of alpha h y h x h transpose xi plus w naught. So here k of x h xi is nothing but just x h transpose xi. So here the sum of alpha h y h x h transpose xi is independent of h. So sum of alpha h y h x h transpose is nothing but w transpose. So the kernel function for a linear kernel is, let's say, something like an identity kernel. Otherwise, this kernelized support vector machine is no longer linear. So now let's consider a linear support vector classifier model using that of the radial basis kernel function. If I click here, we can look at the documentation. Here the regularization parameter is by default 1. The kernel by default is again radial basis function. So I can just ignore this because by default it is radial basis function. I can just declare like this. So here the kernel is RBF. The regularization parameter 1. So here degree 3 something like that. This degree 3 is applicable actually for polynomial kernels. The polynomial kernel just considers all the higher order polynomials up to a certain degree. By default it will be up to the third degree. But in the case of radial basis function, it considers all the possible higher dimensional just degrees. And we have gamma, that's of the scale parameter that we have considered here, gamma, which is going to be estimated. So now let's just fit our model of interest here. I have instantiated this model here, then I can fit by supplying the input data and the output data. Now the model is fitted with the same parameters, regularization parameter 1 and kernel function, radial basis function. And let's see the decision boundary using the plot SVC logistic DB function. So here now this is the kernelized or the nonlinear support vector classifier using radial basis kernel function. So unlike that of the previous case where separating these two classes is not possible, now separating the two classes with a 100% accuracy is possible. Therefore, this is that of the support vector classifier. This line classifies the blue and that of green points with 100% accuracy. If we are interested, we can look at the accuracy of the model svc.score. We can easily observe from the graph, or if we are interested, we can look at just the numerical value by calling the score method under from our fitted or trained support vector classifier. So yeah, therefore 100%. Here, how many support vectors do we have? We can count, for example, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. There are 19 support vectors. So let's just let me take this forward or bottoms. Just let's see the support vectors. I count 19 support vectors. Here we have just 1, 2, something like that, but instead let me count just this length of svc.supports vectors underscore. How much is the length? You see, it's 19. Therefore 1, 2, 3, 19. We have 19 support vectors that determine this support vector classifier decision boundary. So here by default we have used that of regularization hyperparameter of 1. Let's change this, or specifically let's increase it, and let's see the difference in the decision boundary of separating these green and blue points. So here again, let me say SVC. I have to instantiate SVC equals SVC. I just need to here instantiate the model. Now here by default it is C is 1, so I have to change here. Let me make this C equals, no, it should be capital C equals, let's say 100. Now C is 100. Let's train our model, and for that we need to call SVC method. No, I mean SVC.fit. We need to call the method fit and supply the training data. Then it becomes, now it is trained, the parameters, it is 100. So let's see the performance of this model svc.score, supplying input features data and output data. Sorry, here 100%. Now let's plot the decision boundary of this support vector classifier. Now here look, some of the points are inside the margin, but when we increase C, it penalizes misclassification heavily. Therefore it forces the support vectors to be on the hyperplanes standing for the different classes. Therefore here every point is on every support vector for the blue points is on the corresponding hyperplane, and every support vector for the green points is on the hyperplane that stands for the green points. Now here, let's count the number of support vectors. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So, as usual, we can call just here SVC dot support vectors underscore. Here we have the support vectors, but I'm interested on the length, not on the values or number of support vectors, so I need to call this function length 14. There are 14 support vectors that determine this decision boundary. And again, the model's accuracy is 100% because it is able to differentiate the two different classes with no misclassification error. If we are interested, we can obtain also the duality coefficients, but it's not that much meaningful, and we can obtain also the bias using the intercept, but note that this function is a nonlinear function. Therefore, we do not have any weight parameter associated with the covariates. So we can't call, let's say, we can't call like that of the linear support vector. In the case of linear support vector and in the that of logistic regression model, we call the methods the attribute cof underscore, right? But here we do not have any coefficients or weights associated with the covariates included to the model because it is truly a nonlinear function like the one that we have defined. The target function in machine learning model is completely unknown. Therefore, the structural form of the function is completely unknown. So if I call, it says no. Cof is only available when using linear kernel, in which the target function is simplified to a linear combination of the covariates. Similarly, you can obtain the gamma hyperparameter here. So on here it says gamma scale. That's going to be estimated just by calling the method underscore gamma. It is 1.86, and actually if this gamma is small, it implies the kernel is wider. That means each data point influences a larger region. Then in that case, the decision boundary is going to be more smoother. But such a smooth decision boundary could introduce a higher bias. On the other hand, if gamma is larger, that implies a narrower kernel. Therefore, each point affects a small area. If gamma is small, therefore each point affects a small area. And in that case, just the decision boundary is becoming more complex. That means it could have higher variability. So these are just the main concepts regarding a support vector machine, which is the most powerful supervised learning algorithm, and that is applicable for both regression and classification problems. So here, especially in support vector machine, the kernel type is the first hyperparameter, whether it is linear, polynomial, or radial based function. We have to determine the optimal one. And another hyperparameter is the regularization parameter C, which controls the misclassification error balance with that of maximizing the margin. And gamma is also another hyperparameter which controls the influence of a single training point. If gamma is smaller, therefore the point influences a larger region, but if it is larger, a point influences a smaller area. And in general, increasing the regularization hyperparameter C and the gamma hyperparameter may lead to more overfitting. Therefore, these three hyperparameters, the kernel type, the regularization parameter C and the gamma, which controls the influence of a single training point, should be determined using that of a hyperparameter search methods, specifically using that of a grid search algorithm. Therefore, the optimal values, or the optimal kernel type, the optimal value of C, and the optimal value of gamma should be determined through hyperparameter tuning methods, specifically using like that of a grid search algorithm. So this is all about today's video. Thank you for watching.